Homework M6C2 test electric fields. Question number 8, which reads, a hollow metal sphere of radius 30 centimeters is connected to a potential difference of 1.2 kilovolts. Calculate the electric potential at a point 1.8 meters from the surface of the sphere. Now there are two ways to solve this question. I'll cover both of them here. The first way would be to use the defining equation for electric potential and treating this as electric potential 1 at distance 1. We need to find electric potential 2 at a new distance. So if I call this V1, the name of the game here is to calculate V2, the new value for the electric potential. So using the defining equation, V equals Q over 4 pi epsilon naught R naught squared. Revise that lesson if you need to. All we would need to do is plug in all the appropriate numbers to work out what this new potential is. One of the ways to do this is to say that R, the distance for V2, the new potential, is this whole equation is built around the idea that this R represents the distance from a point source charge, or if you're doing gravitation, it would be from a point source mass. So these R's in these equations, and there's many of them that look similar, all of them are measured from the center of the thing. So if it's the sun, it's the center of the sun, and in this case this charged hollow metal sphere, it'll be measured from the center of that hollow metal sphere. So that radial distance for our new electric potential is going to be the distance from the surface of the sphere plus the radius of the sphere. The other thing that we would need is we would need to work out what the charge to use here, the charge stored on the sphere. To achieve that, we can use the defining equation for capacitance. Capacitance is charge stored per unit potential, and we're going to be using the old potential V1 in order to calculate this, and V1 is 1.2 kilovolts. So rearranging that to make Q the subject, Q, the charge stored, is just going to be the capacitance of this hollow metal sphere times the initial potential difference used to put charge on it in the first place, 1.2 kilovolts. So how do we work out the capacitance of a metal sphere? Well, we use the special equation that's designed to do just that. Capacitance of a metal sphere is 4 pi epsilon naught capital R, which is the radius of the metal sphere. So all that's left to do is to say that the radius of the metal sphere is 30 centimeters or 0.3 meters. That goes in there. Once you get a value for the capacitance of the metal sphere, that then goes into this equation, so we can work out what the charge stored on the sphere initially is. And then once we have that charge stored, that's going to be a constant as you move to different distances. That can then be put into this equation to work out what our new potential difference is going to be. New electric potential is going to be at our new distance. And that should spit out a number. The other way to do this is to do it via a proportionality relationship. So if we look at the equation for electric potential and remove everything that stays constant in this question, 4 is a constant, pi is a constant, epsilon naught is a constant, but also the charge stored on the metal sphere remains constant during this story. So that means we can remove everything except V and R, little r, and we end up with a relationship of electric potential is inversely proportional to the distance. So all we need to do now is start with the initial story at a distance of 30 centimeters, 0.3 meters. The electric potential is 1.2 kilovolts. At a new distance of 2.1 meters. Now what I've done there is I've taken the distance from the surface of the sphere and added on the radius of the sphere to get a new distance from the center of the sphere. What would be the potential at this new distance? So in order to do this, we would say that the radial distance has increased by a factor of 7, and because these two quantities are inversely proportional, we would say that the electric potential would decrease by a factor of 7. So that would be, to get from V1 to V2, we would just divide by 7, and then the answer would simply be 1.2 kilovolts divided by 7, and that should produce exactly the same answer.